Section 2.5, zeros of polynomial functions. So what we're going to do is we're really going to greatly expand our tool set here to solve polynomial functions, find their zeros, find where they cross the x-axis. But what that's also going to do is we're going to find the zeros where it crosses the x-axis, the real zeros. We're also going to find the imaginary zeros that do not get represented by crossing the x-axis. Now up to this point, solving polynomial functions, breaking them down into their factors, what we've mainly been using is the idea of greatest common factor, which is really a factoring method. We've also been using inverse operations. Now that includes square roots. And when we are trying to find the zeros of a function, when you take a square root, you do want to look at the positive and negative square root. Now what we're going to do is, these are pretty helpful with your linear, your quadratic, and your cubic functions. But once you get up into 6th degree and 7th degree, these kind of start to get overpowered by the complexity of the polynomial function. So we want to look at some new ways to deal with that. Now the fundamental theorem of algebra, it's pretty important. I'd go so far as to say it's pretty fundamental. That was a joke. Fundamental theorem of algebra, if you have a polynomial of degree n, then it says f has at least one zero in the complex number system. So what that means is that every function, every polynomial function, has a zero, either on the x-axis, real, or not on the x-axis, imaginary or complex. So the linear factorization theorem, if you have a function, you can break it down into individual factors where all of these c sub 1, c sub 2, and so on, they are complex. Now that could mean that they're of the form a plus bi, so they're imaginary, or they could just be a real number. But you can break it down into those individual factors. So looking at a couple of examples here, f of x equals x minus 2. You can solve that using inverse operations. All right? Add 2 to both sides. We're replacing this with 0. And you get a real 0 of x equals 2. Down here, x cubed plus 4x. Well, if we look here, we have a greatest common factor of x. Leaves us with x squared plus 4, set that equal to 0. So we used a greatest common factor, pulled an x out of both terms. And now we have x times x squared plus 4. So that means that x equals 0, or x squared plus 4 equals 0. And what we're using right here is the ZPP, zero product property. If you have a product of terms equaling 0, any one of those terms could equal 0. And then solve from here using inverse operations. X squared equals negative 4, and then we take the square root of a negative. Oh no, that's okay. Square root of a negative means that we just have, oh, I don't need that square root anymore, an imaginary value. So this linear function had 1, 0. This cubic function has 3, has 0, which is a real 0, and then positive, negative 2i, which are both imaginary. But all told, there are 3 zeros, any combination of real and imaginary. So take a look at examples B and D in my completed online notes, or kind of work through those first and then check the answers. Now, if you are not given a problem that is easily factorable, okay, we're going to give you a whole new tool here to kind of break those open. It's called the rational zero test. You have a polynomial function. You have your coefficient, your x value, your next coefficient, your next x value, all the way down to just a final constant. Every single rational zero, which means it needs to be a real zero, can't be imaginary. Every single rational zero, if it exists, is of the form p over q, where p is a factor of your constant at the very end, a sub 0. And q is a factor of your leading coefficient, a sub n. It just so happens that every single rational zero that exists is set up in this ratio. Some factor of your constant divided by some factor of your leading coefficient. So this gives us kind of a starting point to break into these problems. So find the rational zeros of this function. So our constant term, 6. And I'm not going to worry about whether it's positive or negative. Just look at the numeric value, 6. And our leading coefficient, okay, technically there's a 1. So our factors of p are 1, 2, 3, and 6. Our factors of q are just 1. So let's generate a list of all the possible rational zeros. We're not saying all of these are zeros. If the curve crosses the x-axis, it'll be at any of these spots. So our possible rational zeros are all of the values of p over all the values of q. So that'd be 1 over 1, which is 1, 2 over 1, which is 2, 3 over 1, which is 3, 6 over 1, which is 6. And then I said don't worry about whether it's positive or negative because you'll then go in and make them all positive and negative. So now it says use polynomial division with a factor or synthetic division with a 0. Well, we just generated a list of possible zeros. So it's kind of a trial and error. Pick a number you think looks good and see if it works, okay? And it works if it divides it evenly. You get a remainder of 0. So I'm going to use synthetic division, so I'm going to set that up. So let me copy all these coefficients down. So 1, negative 1, 1, negative 3, negative 6. So I'm going to go ahead and try a number and see if it works. So I'm going to start at the beginning. I'm going to try positive 1, see what happens. So I am guessing that positive 1 is a 0 of that function. So let's drop down that first one, and I'll do the bounce and add. So 1 times 1 is 1. Add those together, get 0. Bounce it down, add, bounce it down, add, bounce it down. It didn't work. So I hope you're not using pen, because I'm going to erase all that. Positive 1 is not a 0 of this function. I'm going to cross that out. I'm going to stick close to home, though. I'm going to try negative 1. So drop that first number down, bounce it down, add together, bounce it down, add together, bounce it down, add together, bounce it down. Ooh! Worked. So that means that this graph crosses the x-axis at -1 because that 0 divided it evenly. So I had a quartic, I divided out, now I have a cubic. So here's what I'm going to do. I'm going to do it again. I'm just going to keep dividing this down. So again, it's a guess and check game. I'm going to try +2. Let's see what happens there. So I'll put a 2 out in front. I'm going to drop the first number down. So I get a 1. 2 times 1 is 2. Add those up and get 0. Bounce it. It worked again. Call me butter. I'm on a roll. So I had a quartic. I divided out this 0. I got a cubic. I divided out this 0, and I have a quadratic. Now here's the thing, is this process of synthetic division only works if you have real zeros left to pull out. Kind of thinking ahead a little bit, this is a quadratic. Here's my x squared, here's my x, here's my constant. So I have x squared plus 3. Now if I set that equal to 0, I do not get any more real zeros. Now they just said find the rational zeros. I have them right here. So my rational zeros are x equals -1 and 2. I'm just going to go ahead and write this down. My imaginary zeros, if I move the 3 over, take the square root, I'd get plus minus √3i. Now I had a quartic. 1 0, 2 zeros, 3 4. 4 zeros. Any combination of real and imaginary. Okay? So as you get more complicated functions, here is a way to kind of look at, okay, where can I start? Because there's a lot of numbers on the x-axis you can try, but if you can whittle it down to only 8, that would be fantastic. Okay? Now, as your P and Q values get more complicated, this process may get a little messier. So we have P, which is the number 3, Q, which is the number 2. So factors of P are 1 and 3, factors of Q are 1 and 2. So now let's make all my combinations. 1 over 1 is 1. 3 over 1 is 3. 1 over 2 is 1/2. 3 over 2 is 3/2. And that's where you're going to start. And I'll be honest with you, okay? We live in the 21st century. If you get a graphing calculator and plug this into y equals, go ahead and get a graph and see if it looks like the graph is crossing the x-axis of any of these, and that can give you a better clue as to where to start. So you're not completely stabbing in the dark, you kind of know what you're looking for. That can give you a good place to start. The last little bit I want to talk about is down here. Have you ever thought to yourself, as you're trying to fall asleep at night and you can't, you lay awake, the hours are ticking by, and you're thinking to yourself, I've always wanted to use imaginary numbers in synthetic division. You know, I've thought about that myself. Luckily, you will never be left awake at night wondering when you could do that, because we're going to do that right now. Imaginary numbers and synthetic division. It's actually an extremely satisfying experience, okay? Because a lot of cool things are going to happen, things are going to cancel out. Me personally, I love when things cancel out. So, if we take this quartic, put it into synthetic form, and then they say that 2i is a 0. So I'll put 2i out in front. I hope you're as excited about this as I am, because I'm pretty excited. Let's go ahead and drop that first term. Get a 1. 2i times 1 is 2i, and then you add. Now these are unlike terms, so we have negative 5 plus 2i. Now we bounce down. We have to distribute, so 2i times negative 5, negative 10i. 2i times 2i is 4i squared. And 4i squared, I squared is negative 1. So it's actually negative 10i minus 4. Add these together, 10 and negative 4 is 6. Negative 10i. Now the 2i multiply again. 2i times 6 is 12i. 2i times negative 10i is negative 20i squared. The I squared is negative 1. So that makes that negative 20 into a positive 20. Add together. Ooh. Negative 20 and 20 cancel out. You just have 12i. 2i times 12i, 24i squared, which is really just negative 24. Add. Oh, that's pretty nice, isn't it? Started with a quartic. Now we have a cubic with imaginary components. All right, but here's the cool thing. Imaginary zeros always come in conjugate pairs, because when you take a square root to get the imaginary, square roots always give you a positive 2i and a negative 2i. So let's bounce. Well, drop the 1, then bounce. Negative 2i times 1, negative 2i. 2i and negative 2i cancel out, negative 5. Negative 2i times negative 5, 10i. The i's cancel out, 6. Negative 12i. Today turned out to be a pretty good day, didn't it? And now we are left with a quadratic. This is 1, negative 5, and 6. I'm just going to take this a little bit further. I'm going to put a negative 3 here. 1. Nope, my bad. Positive 3. Positive 3 here. Negative 2. Negative 6. And then lastly, put a positive 2. Drop down. And I have fully synthetically divided this quartic. You probably can't see that. My zeros are x equals 2, 3, and plus minus 2i. You can now sleep soundly for the rest of your lives.